Yeah, my name's Jenny List. I'm here with a bunch of friends from Oxford Hackspace, and I guess some of the stuff I'm talking about here is some of the things we're doing in Oxford Hackspace. I'm here to talk about WSPR, which is a radio protocol, and I grandly titled the piece, I was asked for a sort of a blurb, I grandly titled the piece, "You versus the Atmosphere," as this almighty struggle, so I hope it doesn't turn out to be a disappointment. Now, next slide. I'm going to introduce amateur radio, because I'm guessing there will probably be one or two radio amateurs amongst you, but there'll probably be one or two who aren't. So you'll probably have preconceived ideas of what amateur radio is. You may well have seen things like the Tony Hancock's half-hour radio amateur sketch where he took the piss out of us. I'm afraid some of those things are true. What is amateur radio? It's licensed experimentation with radio. This goes back to between the wars. Radio was just becoming established as technology in its own right. It was the exciting, cutting-edge thing of its day. Radar and all sorts of things like that hadn't yet been invented. And naturally, there were people like us who wanted to experiment with it. And fortunately, governments saw that this had potential to develop a sort of cadre of people who were experts and could produce what became an electronics industry. And so they licensed people like us to experiment with this exciting new technology. We're given specific frequency bands that we can play with, and we can more or less, give or take a few things, do what we want within those frequency bands, as long as we don't interfere with anybody else outside those frequency bands. And we will have to pass an exam to get a license, and when we have a license, we're given a call sign by, in the UK it's OSHCamp, but all the countries have their own licensing body. My call sign's Golf 7 Charlie Kilo Foxtrot. Golf, because it's a British call sign. I think there's G's, there's 2's, and there are M's are British call signs. And Golf 7, because it was a Class B call sign back in the day, from late 1980s. And Charlie Kilo Foxtrot, which is simply a sequential number of digits. I believe nowadays they give out vanity call signs, but back in the day we had real call signs. It's an international, worldwide community. This predates the internet by 60 years or whatever. I believe the only place in the world that doesn't have amateur radio is North Korea. So if you ever find a North Korean radio amateur, you'll have millions and millions of radio amateur geeks queuing up just to have a contact with him because he is the rarest person on the planet. We're rooted in maker culture. Back in the day, you couldn't go out and buy a radio, you had to make your own before the war. And so a huge culture of both making your own kit and sharing your own designs appeared. This is open. I mean, Richard Stallman was probably a gleam in his father's eye at this point. There was no open source movement. People just shared designs. You'll find, if you are a radio amateur, you'll find you're using designs with sort of very old sounding call signs. Like, for instance, you will find people using an antenna called a G5RV that was developed by a bloke in Gloucestershire, 1940s, 50s. And he just shared his design with the world because it was a good design and everybody wanted a good antenna. And there are loads of examples of things where radio amateurs have, between them, developed things, refined them, swapped them around, come up with new designs. And it's, in a way, it's a sort of a prototype for the sort of maker culture that we all know now. It's a multifaceted pursuit. Now we come back to the Tony Hancock thing. Unfortunately, there is a certain type of radio amateur who gets their license, goes out and spends £1,000 on a very fancy Japanese box of tricks and fancy antenna and thinks they're the dog's whatsits because they work the world. And they will often think, oh, I've got a very old call sign with my Japanese rig and my fancy antenna, so I can look down on you who've got a new call sign, but you build your own kit and I don't. Unfortunately, it's all true. I mean, if you go down onto 80 meters on a weekend morning, you'll find endless old gits talking about the war and their allotments. But fortunately, it's a multifaceted pursuit. There are as many different things to pursue in amateur radio as there are radio amateurs. okay, some people go out and buy fancy rigs and collect countries around the world to work. Great, that's their thing. My thing is building toys, building little boards and tiny little transmitters. I don't really care if I never work anybody. Half the transmitters I've made, I've sort of proved they work, and yeah, I've made myself a little rig and never worked anybody on it. But that's my thing. Somebody else's thing will be something completely different. You probably won't hear this said very often, but now is a very exciting time to be a radio amateur. Because traditionally it's an analog thing. I mean, there will probably be many radio amateurs who will go, aha, no, because obviously the basic form of radio amateur is Morse code, which is very digital. You even use a finger. But traditionally all the circuitry has been analog. You know, you'll have an analog receiver, you'll hear stuff in the speaker, whatever. It's a very exciting transition at the moment because you're moving to digital. You're moving to software-defined radio, software-defined transmitters, software-defined receivers. You're moving to wonderful chipsets designed for other things that have loads and loads of cool applications in amateur radio. I was, for instance, looking at a chipset designed for those 430 megahertz remote control things a week or two ago. And for 79 pence, you basically get a software-defined 70 centimetre amateur radio transmitter. How cool is that? And so all this kind of stuff make it an exciting time to be a radio hacker. At least I think so. So hang on, next slide. Radio propagation. Now, there's a problem with radio. It's an electromagnetic wave, like light. And if you were in free space, out in the deep black of beyond, it would just go in a straight line. So if you can see the transmitter, you can receive it. Now, unfortunately, the Earth gets in the way. And everything beyond the horizon, if you can receive it, you're not getting a straight line path. You're getting some interaction with the atmosphere. It's being bounced off the atmosphere. It's being bent round the Earth. There are multiple different ways that radio get from A to B. It's not just a sort of a foregone conclusion that when you hit the button on the transmitter, it will reach the other person. It depends on all the factors of the atmosphere. It depends on the power of your transmitter. It depends on the weather. It depends on the terrain. And this is the problem that faces radio amateurs. And this is one of the facets of amateur radio that many people get seriously into, just mapping propagation. Next slide. Which brings me on to this guy, Joe Taylor, K1JT. The Americans have vanity two-letter call signs. He's obviously got his one. Now, Joe Taylor is a scientist. He's a Nobel Prize-winning astrophysicist. I think his, was it something to do with pulsars? I think his Nobel Prize, you'd have to look it up. I'm afraid I don't know on that one. He is his special interest is radio propagation. And he's developed a whole series of digital radio modes, transmission modes, basically ways of encoding stuff onto radio waves, which are designed specifically to test the limits of radio propagation. So to get contact from A to B with usually minimal stuff like just your call sign and where you are, with the minimum power possible, because he's wanting to push the boundaries of science. And this is important because there is a scientific aspect to what I'm about to talk to, which is which is WSPR. He developed WSPR as latest at the time in one of a series of protocols in 2008. Now, WSPR, which is the nub of this talk, Weak Signal Propagation Reporter. It's a beacon mode, which means that you don't sit and operate your WSPR rig into the night. You turn on a box, turn on your computer and go away and make a cup of tea, or go up to Hebden Bridge and do a talk. If you were to type Golf 7 Charlie Kilo Foxtrot into the website I'm about to show you, you would find my WSPR beacon sitting there talking to the world, and even, I hope, some people hearing it. It's a binary format, so you take your call sign, in my case, Golf 7 Charlie Kilo Foxtrot, your power, because you want some parameter of how far is this getting on what power. So your power in dB milliwatts, which is a ratio of your power in milliwatts. your grid locator, which is it's best described as the national grid for amateur radio. There is a worldwide grid, which is a formula for turning latitude and longitude into a string of numbers and letters. For instance, my home location in Oxfordshire is India Oscar 91 Lima Whiskey. And I should have really have looked up the location for this one and had it pat, but there you go. So you have those text string, call sign, power, grid locator. It's encoded and compressed into 50 binary digits. That is encoded onto the radio wave using frequency shift keying. So one frequency is 1, one frequency is 0. Now, what makes WSPR special? 6 hertz total bandwidth. Now, 6 hertz is tiny. If you listen to a WSPR transmission on a radio, you'll hear a tone. Beep. You will not hear that change. You know it is changing 50 times in a packet, but you won't hear it because your ear just can't register 6 hertz. Now, a typical speech transmission will be about 2.5 kilohertz, so that's 2,500 hertz in width. So when you're listening and you're hearing that, you're actually hearing a 2,500 hertz slice of radio. Now, to get heard in that 2,500 hertz, you have to puke out a lot of power from your antenna for the guy at the other end to hear it. Now, the whole point of having a 6 hertz bandwidth is because it's such a tiny slice of radio you're listening to, the transmission power required to get heard at the other end is also relatively tiny, which basically what makes WSPR so interesting from my point of view for mapping propagation. It's very, very strict timing in WSPR. Your transmitter would have to be synchronized to world time. People will do it with a GPS receiver. I do it with NTP over the internet. So typically a WSPR transceiver will be connected to the internet because it's the quickest way to do it. And every even UTC minute, every WSPR transmitter in the world will start transmitting. It takes about a minute and 50 seconds to transmit the whole packet of data. Now, this at the bottom can survive a minus 28 dBm signal-to-noise ratio. That basically means it can hide in the noise, you wouldn't hear it, and the computer can still detect it. It can survive conditions where you simply wouldn't be able to even know that there was a station there if it was a voice station. I borrowed this table from Carol Milazzo, KP4MD. She's done quite a lot of presentations on WSPR in the States, so didn't actually have a license on her website, so I may have nicked this, but I hope she won't mind. This compares the amount of power you'd need to do the same job with various different radio modes. At the bottom, you've got single sideband. That's your speech radio that most radio amateurs use. Underneath, you've got teletype, which is the oldest digital mode. Imagine that as like a 50-baud modem connected to a radio. Below that, you've got Morse, CW, continuous wave, and then you've got several different varying digital modes. That's a JT, Joe Taylor mode, same guy who developed WSPR. And at the bottom, you've got WSPR. Now, on this side, you've got the equivalent power that you would need. So to get the same distance in single sideband on a given frequency, you'd need 25 kilowatts to what you'd need 5 watts of WSPR. So as you can see, WSPR is a very, very efficient way of getting radio waves around. Now, I find it's kind of funny. Carol Milazzo's American. She thinks 5 watts is a small power. It's about 500 times the amount I use for my WSPR transmitter. WSPR's great. You can talk great distances with tiny power, but what makes it really powerful is a big data aspect. Every WSPR receiver is connected to the internet, and every time it hears something, it sends that into a centralized database. This happens to be a map that I grabbed from the screen earlier in the week. There's me, Golf 7 Charlie Kilo Foxtrot in Oxfordshire. And I've got pretty tiny power on 20 meters, which is 14 megahertz. So I'm not getting across the world, but I'm instantly, just on an ordinary day, getting all the way across Europe. Now, I think this is why Joe Taylor did it, because he's a scientist. He wants data. He doesn't want to say, I've worked to these countries. He wants to gather data. He wants to model the atmosphere. And this is, to me, is where WSPR becomes really powerful, because every spot gets uploaded. It's been running for 6, 7 years, something like that. And there are now, was it 320 million spots in the database when I looked earlier in the week, and it's going up by about 350,000 spots a day. So that's a huge trove of data, and of course it's all downloadable. So open source, you can do what you want with it. If you are interested in the atmosphere, in the properties of the atmosphere, you've got an enormous trove of year upon year of atmospheric data ready to play with. And that makes it very, very powerful indeed. You can say, okay, I know that there's a high pressure coming up from the Atlantic, and you might say, hey, I know from experience that that means I'll get a particular lift in a particular direction. But now you can model that. You can go to the data and say, right, find a time in the past when a similar high pressure or whatever, or a similar time of year, or a similar auroral event, or a similar ionization of the atmosphere, and model on real data. This provides you with an unbelievable trove of data that you would never have had in the past. That's the extra angle that the internet brings to otherwise a fairly dry radio protocol. So how do you do WSPR? WSPR's, at its most basic form, distributed as a piece of software. It's a GUI package, Mac, Windows, Linux, GPL'd. It works through your sound card. It's connected to a single sideband transceiver, typical radio amateur might have in their shack. It's a software-defined radio, but probably not as you would understand it. What a single sideband receiver does is it takes that little 2.5 kilohertz slice of radio and shifts it down to audio. So effectively, if you listen on a sound card, you can do all your software radio maths on that audio, and you've basically got a software-defined radio that works on that little 2.5 kilohertz of radio. So what you're seeing here is a waterfall. Each one of these slices is 1 whisker per packet, so 1 minute and 50 seconds. That is 200 hertz wide, the 200 hertz segment of whichever band that it happens to be tuned to at the moment. And each one of those lines is a WSPR packet that this receiver has picked up. And the really cool thing about it being software-defined radio is it doesn't have to listen to just one. It can have 20 different packets appearing, and sometimes you will see stripes like this with lots of packets, and it will log them all. And because they're only 6 hertz wide, they're all on different frequencies, and the maths is quite up to spotting them. It's got 1 minute and 50 seconds in which to do it while it's receiving the next one, after all. And a lot of people will just leave this running in their shack. Personally, I don't like doing this because it means I have to leave a radio, a computer, and various other things running, and I think it's a power hog, but that's what people do. And it's a perfect example of what I was talking about amateur radio being in an exciting position of software-defined radio starting to appear. 25 years ago, when I got my license, software-defined radio didn't even exist. I mean, if you were probably the military or something, you probably had some incredibly expensive kit, which probably isn't even near what you can buy for 100 quid nowadays. Technological advancement has given us the ability to do what is quite hefty computing on an ordinary commodity desktop, which opens up whole new vistas for an old pursuit. This is more my kind of thing for WSPR. If you have a tiny protocol, it makes sense to have a tiny transmitter. You don't need a thing capable of kicking out 100 watts and talking to Australia with SSB, when all you want to do is kick out a few milliwatts. These are a couple of commercial ones. They're both based on embedded microcontrollers. That one, I think, is a PIC, but it might be an Atmel. But it's using a direct digital synthesizer module to basically generate RF directly. The one below is a PIC and a voltage-controlled oscillator. they're both different ways of achieving the same thing. I think those cost in the region of sort of 20 or 30 quid. I think that one, if you buy the display board, costs closer to 50 quid. But these are just buy the kit, solder it up, plug it in, connect an antenna, and off you go. The power is so tiny, you don't even need to worry about the antenna being tuned. It'll just work. It's great. This is what I use. I use Raspberry Pi. A Raspberry Pi comes with a really neat piece of hardware. It's got a clock generator, which is designed to provide clocks for external peripherals. But effectively, it's a synthesized RF source that will work from low kilohertz up to about 250 megahertz. And it's just a 3.3 volt I/O line. But a 3.3 volt I/O line can sync about 10 milliwatts. And 10 milliwatts, as you saw earlier from my little map there, can get you into an awful lot of places. I made a little board. I actually put this on Kickstarter. It's a prototyping board for experimenting with radio with the Raspberry Pi. Unfortunately, it didn't make it on Kickstarter, but this isn't actually such a bad thing. I'll tell you why it didn't make it. I thought I can make 200 of these, and about 180 people decided they wanted one. But there's a lot to be said for having a Kickstarter that fails, because, of course, if your Kickstarter succeeds, you actually have to ship the thing. Whereas if it fails, you just say, oh, well, I really put work in, but you don't have to do a damn thing. I am pursuing putting that on sale and producing a version 2 with slightly different I/Os and a little bit more prototyping space, but that will be sold on an individual basis, so I won't have Kickstarter do my hard work for me. On there's a circuit that is a low-pass filter. It's an LC network. Effectively, it gets rid of frequencies above a certain amount. The reason for that is the Raspberry Pi kicks out square waves, and one of the properties of square waves is you get the frequency you want, you get twice the frequency you want, you get 3 times the frequency you want, and that's great. You just better hope that your local airport's emergency channel or your police or whatever aren't on one of those harmonics. So that's one of the reasons why they make us do an exam to get an amateur radio license, is to teach us that you've got to do things like that. Oh, running out of time. I didn't write the software. Off the shelf, just download it from GitHub, Whisper software, just a command line, you just run it, job done. If anybody fancies rewriting it to work with the Raspberry Pi 2, you're a better coder than I am. It phones home to use NTP to get the frequency bang on. Yeah, I've covered all the other things on there. I put together a more information thing. If you're interested in amateur radio, Radio Society of Great Britain is your first stop. They like to style themselves as they run amateur radio, but they're basically the old farts who like to think they run amateur radio. Maidenhead grid locators, that's the grid system used in Whisper. It's called Maidenhead because there was a conference in Maidenhead where they decided which system they were going to use. Whisper, that's K1JT's, Joe Taylor's homepage. WhisperNet, that's where you can mine the data. You can type my call sign in and see how little I've worked. Some quite interesting stuff. People have ported Whisper for Arduino and PIC. There are quite a lot of things out there on the internet to build your own if you're interested. And there's Raspberry Pi, the thing I use. I'm Jenny List, Jenny Alto on Twitter. That's my website, languagespy.com. Eventually, you'll be able to buy that little board there. It's a bit confusing. I set up in business. I spent the last 5 years working with dictionary data for Oxford Dictionaries. So my business is actually a language technology business. But you've got to bring some money in somehow. So I've started producing amateur radio kits. It's funny how things take you. So that's why it's languagespy.com. So I hope that's been illuminating.